In today's artificial intelligence class, we will see the robotic software architecture from 5th unit. Under this class, we will see the subsumption architecture by using the augmented finite state machine for robot with 6 legs, this one. After that, the 3-layer architecture. The 3 layers are the reactive layer and executive layer and deliberative layer. After that, we will see the pipeline architecture for autonomous robot car, this one. Okay, we will see all those things one by one. Robotic software architecture. What is software architecture? It is nothing but the methodology for structuring algorithms. Okay, for particular application, n number of algorithms will be there. Okay, all the algorithms will be arranged in particular order, okay, in particular fashion. That is called as the software architecture. In what way the algorithms will be arranged or connected, right? The architecture includes languages and tools. Okay, so it is software architecture. So the software programming language, which language we are going to include, and the tools. Tools is nothing but for example the library set or some additional ready-made tools by which we can easily construct the program. Okay, so these two are very important in software architecture, that is which language we are choosing and which tool we are implementing. All those things are important. Apart from that, the philosophy of how the programs can be brought together. Okay, how the software programs, for example this is program 1, program 2, etc. So in particular software application many number of programs will be there. Now the philosophy for how the programs been together is called as software architecture. Okay, here the software architecture for robotic must decide how to combine reactive control and model based deliberate planning. Okay, deliberate means the thoughtful planning. Okay, so we have to combine the reactive control and the model based deliberate planning is called as robotic software architecture. These reactive control and deliberate planning technique have its own strength and weakness. First, let us see the reactive control. The reactive control is sensor driven. Sensor is a device which is used to perceive the environment, isn't it? So it is a sensor driven and it is suitable for making low level decisions in real time. Okay, so currently it will perceive the environment, accordingly it will take some decisions. So this is low level decisions. Okay, but when come to global control decisions, global level decisions, this is not suitable. Okay, so these decisions depend on information that cannot be sensed at the time of decision making. Okay, so the reactive control is used to make decisions at lower level, okay, in the real time. So in this situation, that is taking decision at the global level, we can use deliberate planning technique. Hence, the robot architecture uses reactive technique for lower level decision making and deliberative planning technique at higher level decision making, right? And nowadays these two techniques will be combined to form the new robot, and the combination of these two is called as hybrid architecture. And next let us see the different types of software architecture for robotics. The first one is subsumption architecture, and second one is 3-layered architecture, and third one is pipelined architecture. So when come to subsumption architecture, we will see the augmented finite state machine for robot with 6 legs. And when come to 3-layer architecture, the 3 layers are the reactive layer, executive layer and deliberative layer. When come to pipeline architecture, we will see the architecture for autonomous robot car. The subsumption architecture, which is introduced by Brooks in the year 1986, it is a framework for assembling reactor controls out of finite state machines. That means the reactor controllers are attached to the finite state machines. So the finite state machine which contains nodes and arc. The nodes in the machine which contains test for certain sensor variables. Okay, So the sensors variable will be tested by the nodes and the arc which are tagged with messages. Okay, so the arcs will tagged by messages, every arc which contains message. So when the robot traverses in that particular arc, then the message will be sent to robot motors or the finite state machines. Okay, whenever we traverse to a particular node through the arc, we will get these messages. And the finite state machine process internal timers. Okay, that is nothing but clock which controls the time it takes to traverse an arc, right? So the traverse will be controlled by the clock, hence this particular machine is called as augmented finite state machine or otherwise called as AFSM. Okay, so finite state machine will become augmented finite state machine when we implement the clock. And now let us see an example for this augmented finite state machine, right? Here we are having robot with 6 legs. See, the robot is having 6 legs, 1, 2, 3, 4, 5, 6, but we are going to implement this AFSM for only a single leg, right? So for lifting any one of these legs, 2 motors are there. By using 2 motors, one single leg will be lifted and it will move forward. The robot will move forward, right? So based on the feedback from the sensor, this ASFM will react. ASFM means the augmented finite state machine. Okay, the finite state machine will work based on the sensor feedback. If leg is struck, okay, it cannot move forward. If leg is stuck, some object may be here so that it cannot move forward. In that place, what it will do, the leg will lift somewhat increasingly higher. Okay, it will lift somewhat increasingly higher so that it can easily move forward, right? So the AFSM implements cyclic controller. Okay, see, this is the finite state machine for robot with 6 legs, and this will control only a single leg. If this is a cyclic controller. Okay, the forward sync space rely on sensor feedback. So based on the sensor feedback only, the forward relay will be taken place. And if leg is struck, that means it is failed to execute the forward string. Okay, leg is struck means it cannot move forward, that is failed to execute forward swing. Okay, so the robot reacts the leg, it lifts up the leg little higher than the previous one or normal one and attempt to execute the forward swing once again. Okay, so that it can move easily forward. And this is the simple finite state machine for a robot. This particular robot, 6 legs robot, but this is used to control only a single leg. Okay, so this diagram is used to explain how the robot single leg will swing. Swing means it will move backward and forward. Okay, this is called as swinging. So this is initial state. So from the initial state, it should push backward. So the leg will push backward and it will move to S2 state and lift up. From the back, it will lift up. The leg will be lifted up. Then it will move to state 3. So then it will move forward. It tries to move forward. Okay, if there is any struck here, then it will lift somewhat higher. Okay, then again tries to move forward. Okay, then it moves forward. There is no struck means it will go to state 4 and sit down. Right. So this is what a very simple finite state machine for a single leg, controlling single leg for a robot. And now it is important to synchronize all the finite state machines. by combining the output values, and these output values may be conflicting sometimes, because if we implement all the AFSMs at the same time, conflicts may occur, right? So it enables the programmer to compose increasingly complex controllers in the bottom of fashion. Bottom of fashion means first the finite state machine will control one single leg, and it may tries to control 2 leg, 3 leg likewise. Okay, and it begins with the machine for individual leg, followed by coordinating multiple legs in the increasing order, right, and implementing this higher level behavior such as collision avoidance. Okay, why collision avoidance is important? Because at the same time so many legs will move, that is tries to swings, means the collision may occur. Okay, so collision avoidance should be implemented here. So as per our example, our robot is having 6 legs, and 2 independent motors are there to control a single leg. So totally 12 dimensions are there for configuring only legs, and 6 dimensions are there for this location and orientation in the environment. Okay, so totally 18 dimensions. Totally 18 dimensions are there. Now our algorithm tries to find the path in high dimensional space, right? So the robot wants to move from one location to another location. We have to control all the 6 legs as well as the location and path orientation, right? So but the robot may sliding down a slope. So if there is a slope, means there is a chance for fall down this robot, right? Because such stochastic effort, a single path through the configuration space is too hard. We need to find multiple spaces, multiple paths otherwise. Okay, so generating motion behavior is too complex for robot motion planning algorithm. The problems or difficulties in subsumption architecture. So there are 3 problems. The first one is the AFSM are driven by raw sensor input. Okay, so based on the raw sensor input only it will designed. If the sensor data is reliable and contains all necessary information, then only the decision making will be very correct and it will works well. Otherwise it fails, right? If there is no necessary information, means immediately this will fail down. Okay, the subsumption trial controller have applied for very simple task, that is the robot will follow a wall or moving towards a visible light source, then it will work well. Okay, otherwise if the robot is implemented in very complicated environment, it cannot move forward, right? When come to the second one, the lag of deliberation means discussion otherwise. This makes difficult to change the task of the robot. Okay, so this is the second problem. When come to third problem, subsumption style controllers tend to difficult to understand. Okay, that is the complicated interaction between dozens of interacting this AFSM, okay, finite state machines, and the environment, complicated environment. Suppose if we implement the robot tries to move on complicated environment, it is very difficult. Okay, for all these reasons, the subsumption architecture is rarely used in robotics. So this is somewhat failed one, but it is very much influence on other architecture and individual components of some architectures. Okay, this is the very basic foundation of robot movement, right? The 3-layer architecture, it is used to overcome the failure of subsumption architecture. Okay, so this is hybrid architecture which combines reaction and deliberation. Right, the most popular hybrid architecture is 3-layer architecture, which consists of the first one is reactive layer, and second one is executive layer, and third one is deliberative layer. In the three-tier architecture, the first one is reactive layer. The first layer is reactive layer. This layer provides low-level control to the robot, right? Low-level control, and it is characterized by tight sensor action loop. The sensor action loop is very tight. So based on the sensor only the action will be taken place, and the decision cycle is often on the order of milliseconds. Okay, so immediately the decision will be taken place by the robot. The second layer is executive layer. See, this is the executive layer which combines the deliberative layer as well as the reactive layer. Okay, so it accepts the directive from deliberative layer, that is from deliberative path planner. The path planner is actually located in deliberate layer. It accepts all the directives, and the directives will be sequenced to them by using this executive layer, and then that will be given to the reactive layer, so that the robot will react based on these directions. The decision cycles at the executive layer are usually in order of second. Okay, so immediately the executive layer will order all the decision cycles and then given to the reactive layer. And another responsible for this executive layer is the interacting sensor information into internal state representation. This is most important one, that is it may host the robot's localization and online mapping routines. Okay, accordingly the movement will be taken place, isn't it? So executive layer is somewhat important here. The third and most important layer is deliberative layer. It is otherwise called as planning layer. Okay, it generates global solution. It generates global solution to complex tasks by using planning, right? Hence, this is most important one in the robotic software architecture. And this decision cycle is often in the order of minutes, because the decision is more complex one. It takes more time. And this deliberate layer uses models for decision making. Okay, so by using this model only the decision will be taken place, and this model must be either learned from data or supplied by the robot. The data will be supplied to the robot, or by utilize state information which will be generated by executive layer, isn't it? So by utilizing state information by the executive layer, the decision will be taken place. Okay, so the model will be based on either by the external data or by the state information from the executive layer. Most of the modern robot software architecture uses only this three-layer architecture, and some of those software system uses additional layers also. For example, the user interface layer may be included in this architecture, which is used to control the interaction with the people, okay, with the human being. So this is user interface layer, and the multi-agent level which coordinate the robot actions. So for control the robot actions, multi-agent may be required. With that, the other robot operations in the same environment is also taken place. Okay, for example, if a robot want to work on a complex environment, a single agent is not sufficient. Hence, the multi-agent level architecture is also implemented here. The next one is pipeline architecture. This is another robotic software architecture. It combines the subsumption architecture and three-layer architecture, because the process will execute parallel in this pipeline architecture. Pipeline means all the process will execute simultaneously, isn't it? So it combines the architecture of subsumption as well as the three-layer architecture. Here let us see the pipeline architecture for autonomous car. Here a data pipeline in which all modules process data simultaneously. By using data pipelines, all modules will process the data simultaneously. Here we are having different types of modules. For connecting all the modules, the data pipeline is used. In this autonomous car architecture, different interface layers are there. First one is sensor interface, perception interface, planning and control, user interface and vehicle interface. After that, global services are also there. Here the data enters into the pipeline at sensor interface layer. First the data enters into sensor interface layer because sensor will act as an input, isn't it? And next the perception layer will take in those data from sensor interface and it updates the robot's internal models. It updates the robot internal model of the environment based on this data. Okay, again this data will be given to planning and control layer, isn't it? So here it will adjust the robot internal plans. Okay, the planning layer will adjust the robot internal plans and turn that plan into actual control for the robot, right? So this is the planning and control interface layer. And next one, all those things will be communicated with the vehicle interface layer. Vehicle interface layer is here. The key concept about pipeline architecture is all happen in the parallel, that is at the same time. Here the sensor interface, perception, planning and control, user interface, vehicle interface and global service, all the layers will execute simultaneously, right? The perception layer which uses the most recent sensor data and the control layer which uses somewhat slightly older data, because after the perception execution only the data will be given to planning and control layer, isn't it? But the perception, planning act all at the same time, everything will be done at the same time. So this is called as pipeline architecture. The advantage of pipeline architecture is this architecture run asynchronously, that means all the layers are independent to each other and all computation is data driven, that is the data pipe will be connected to all the layers, right? Hence it is very fast architecture. The pipeline architecture is the fast architecture and it also contains other cross-cutting modules, which is responsible for communication between the different elements of pipe, right? So the cross-cutting module used to communicate the different layers by using the pipelines. So far we have seen the software architecture from 5th unit robotics, and we have seen so many different software architectures, that is subsumption architecture, 3-layer architecture and pipeline architecture, and for all these things we have seen the suitable example also. In the next class we will see another important topic from 5th unit. For more information please go through your textbook. Thank you.